Hello everyone, my name is Raina and I am the Teacher Development Manager for Macmillan Education International Curriculum. Today we have Pat Dower with us, who is the Max Science author, and he will be delivering a webinar for us about inquiry-based learning. So I will send it through to Pat in a moment. Just to be aware, please keep your mics muted, and then at the end of the session, you'll have an opportunity to ask any questions that hopefully Pat will be able to answer for you. So I'm going to hand it over to Pat, and hopefully please make sure that you are able to hear us. If you can just let us know in the questions box that you can hear us clearly, that would be great. And I'll pass it through to Pat.
Thank you very much, Raina, and hello everybody. I'm looking for some sort of response in the questions box to say yes, we can hear you. So as Raina said, it's inquiry-based learning, and more specifically scientific inquiry, that we're going to cover in this webinar. Raina, nobody's answered to say they can hear. Shall I just keep? I'll keep talking for now, and I can always start again if you tell me there's something wrong. So. Yeah, inquiry-based learning and scientific inquiry. So it's really useful to, so we're going right. It's really useful to think of scientific inquiry as a process and not just an activity. So I'll explore that a lot more as we go through. So during the webinar, our four main things that we'd like to cover are an introduction to scientific inquiry. What is it? How scientific inquiry helps the learners to operate like scientists, to think like scientists. So we're making a distinction between having a massive body of knowledge, that is science, and actually thinking and working as a science. So the skill set that goes alongside that. Then we're going to look at different types of scientific inquiry. Very commonly you find schools very familiar with one sort, less familiar with the other. So make sure that you can do the full range. And then we'll think about the balance between doing and learning, because it's quite easy to have a very, very busy, vibrant classroom, kids doing all sorts of wonderful activities, and hopefully they're learning as well. And it's about getting that balance between activity and learning right, because they go hand in hand. Okay, and click on. So first of all, we need to be a bit more specific. What do we mean by scientific inquiry? So you can do the searches yourself, but the neatest definition that seems to be around at the moment is, I'm thinking of it from the learner's point of view, is that scientific inquiry is what learners do in order to try and answer scientific questions. I hope that's all good. Oh yes, and look, somebody said they can hear me. So thanks, Karina, if I read that right. That's a relief. So I might be broadcasting to one person, Raina, but okay. So we need to maybe unpick that, what is a scientific question as well, and think about how this fits in the broader thing of inquiry-based learning. So bit of jargon, a few terms to think about there. So inquiry-based learning first, so that's sort of the core philosophy that underpins the Max Science series, of which I'm an author on, and and what underpins inquiry-based learning? Well, a huge amount of research, and we'll have a look at why it is so effective and what supports it as an approach. So just to say what inquiry-based learning might look like, imagine we were teaching a class about plant growth, and compare these two styles. So style one might be, hold on, let's press the right key. You tell the children that plants need light, water, possibly nutrients from the soil, maybe from somewhere else, in order to grow. That would be instruction or transmission style teaching. Or you could approach it through a question. So you pose the question at the start of this topic, and that is, what do plants need to grow? And that's your launch point for inquiry-based learning. So there's our question, and let's think of the sort of things that might erupt from this question there. So first of all, asking the children and thinking of yourselves, well, what ideas do I already have about plant growth and what they actually need? better if you can start from where the learners are and build from there rather than starting from zero when they don't need that. And also it'll expose their misconceptions as well as what they need to learn about next. Then you might think, well, let's put the learning in context. Why does it matter? Why are we bothered about plants? Well, we might be bothered just because we're curious, and that's great. We've definitely encouraged that. And also, we might be interested in plants because they are the source of all food on this planet. So quite important, really. So in any science, I always like to put that learning where it sits. What's the use of this? What's the point of what we're learning? How does it apply to the real world and to other things? Then it's right. How could I find out an answer to that question? You know, what sort of investigations, inquiry could I do? Then that'll lead you. What other things might be interested in this topic? So, well, is it possible to live without plants? Are there food sources that don't depend on plants? What would the earth be like if there were no plants at all? Those sorts of things. And learners are great at coming up with those. You don't always answer them at your first hit in a science lesson, but it's great to give them a chance to question. Then you think, right, we've discovered all this stuff. How are we going to tell other people? We found some really interesting stuff. We're going to present it, write it, draw it, graph it, do a broadcast, and so on and so forth. A very important skill, and that sits within the umbrella of inquiry-based learning. How could I use my learning in other situations? And you'll see that as a recurring theme in anything we learn in science and other subjects for that matter as well. If you can take the skills that you've got and the knowledge you've got and use it somewhere else in a novel situation, that is super useful. That is real life. That makes you employable. And very importantly, sort of completing that, if you look diagonally across the slide, you started off thinking, well, what do I know already? And then at the end of this process of inquiry, you think, well, what more have I learned? What of my old ideas don't apply anymore? What have I had to change? What have I had to completely throw out? So I hope that gives you a feeling of inquiry-based learning. So I've mentioned the evidence as to why we chose, when we're developing Mac Science, to use inquiry-based learning as its base is, first of all, it does make much better use of prior learning. Students find it a lot more engaging, particularly as they get older. And then what you tend to find, there's a lot more thinking involved, not just memorizing. So you often get far deeper learning with an inquiry-based approach in the end. Maybe not straight away. You can feel a bit discouraged sometimes, but in the end you do. And then the last but one bullet point is these range of skills about being adaptable and resilient and can tackle a wide range of situations. And then, of course, the last one, onto working in teams collaboratively. Again, that real life. So children who've learned through inquiry-based approaches are certainly better prepared for their world, for their next stage in their lives, and for their lives as professionals and as adults, than if they've had inquiry-based, compared to if they've just learned a big body of knowledge, which might have changed by the time they're adults anyway. Okay, we talked about a scientific question. So scientific inquiry is what we do to try and answer a scientific question. So what is a scientific question? This is the last of the definitions for now. You'll be glad to know. So scientific question is one that you can do tests, activities, investigations to try and find an answer to. And the other criterion that would make it a good scientific question is it's focused and it's clear about what you're trying to find out about. So an example of that might be an unscientific question. If we're thinking about the sky, you might say, what's the sky like? Not very scientific, it's not very focused, hard to say, well, what investigation am I going to do exactly? But if you ask something a bit more focused, it would be better. So what makes the sky appear blue? Right, okay, we've focused that down, and we can now maybe start to think of things that we might actually investigate, measurements we might take, get our telescopes out, and so on and so forth. So you see the difference between a less scientific and a more scientific. Okay, a job for you. What I'm going to do is put up 3 pairs of questions. Each pair is focused on a topic. One is a better scientific question than the other. So all you have to do is write down the number of the question that you think is the better scientific question from each of the pairs. So first pair of questions. Are lions fast, or can a lion run faster than a human? So you type 1 or 2 depending on which you feel is the better scientific question. Great. I'm seeing lots of 2s. I hope you're happy with that. If you didn't type anything, that's fine. So let's have a look at the next one. So you see with it is more focused. Are lions fast? What do you mean by fast? So there's a problem straight away with that. Whereas number 2, it's a comparison. You can say, yes, one is faster. You can take measurements. You could brace them against each other, however you're going to do it. Okay, next pair. Will a rock break if a 100-kilogram person stands on it? Or is it easy to break rocks or locks? Okay, so mainly 3s, couple of 4s. So with number 4, what do you mean by easy? What might be easy to Rainer, because she's very strong, might be hard to me if I'm not as strong as Rainer. So it's a bit vague. But if we've done something a bit more focused, so right, we're going to put 100 kilograms weight on this rock and see if it can take that weight. We're a bit clearer. We can do a test on that. So 3 would be the better scientific question. Well done to all the 3s. And last one. What is a farmer's field like? Or where do weeds grow in a farmer's field? Seen Brian come up with a 6 and Joe, yeah, lots of 6s. Oh, they're flooding in. Yeah, so yeah, that seems the popular one there. So more focused. Okay, so those are scientific questions. So part of scientific inquiry for the kids is getting them to ask questions that they can investigate and refine their questions. It doesn't happen automatically. You will need to help them when you get in them to come up with their scientific questions, which is a very good thing to do. You will need to support them in making them a bit more focused and refined. So you'll just see a box popping up there. So there's an additional resource that comes as part, is available as part of Mac Science, skill sheets, and there's one in stage 2 specifically on asking scientific questions to really unpick the skill a bit more and support the learners. Okay. I mentioned about scientific inquiry being a process, not an activity. So what I'm going to do now, I'm going to be daring. I'm going to try and do it live here. So you'll see the picture that I have 2 balloons inflated to different amounts, and they're connected by a plumbing tap just from a DIY plumbing center. And at the moment, the tap is closed in the picture. Excuse me, so the air is trapped within the balloons and it can't flow from one balloon to the other. So nothing's happening at the moment. And the question is what do you think will happen when we open that tap? So air is now free to flow left to right, right to left, whatever way it wants. Yeah, I'm actually going to say what I'd like you to do while I get my balloons ready to actually show you this. I'd like you to have a think. Try and say it as fewer words as possible. Just have a think. What do you think is going to happen when I open that tap and air can move left to right. Can't escape, it's still trapped within the balloons. Right, bear with me while I get my balloons ready.
Okay, so what we have here is two standard party balloons, inflated different amounts, as you can see, and they're connected to a tap. At the moment the tap is closed, so the air is trapped within the system and cannot flow left to right, right to left. So the question is, I would like you to predict, what do you think is going to happen when we open the tap? No change. Is air going to flow one way to the other? One balloon get bigger, one balloon get smaller? Are they going to equal? Whatever. So I'll open the tap now. Most people are surprised by that, including very, very experienced science teachers. And the simplest science behind it might be thinking, what is it like to blow up a balloon from the start? And you probably recognise that when you blow up a balloon, it's really hard to get it started. It's really hard to start the rubber stretching. So the smaller balloon was in that phase where the elasticity of the balloon was creating a higher pressure in that balloon. This one, that's at the stage of, you started it off, the balloon's now much bigger. You know, when you blow it, the balloon's going, it blows bigger and bigger, it's easy, and so the rubber is stretching more easily. So the inward force from the rubber is less, and so the pressure inside that balloon is less. So even though the volume is greater, the pressure is less, and it's pressure which is the trump card here. So when we open the tap, the air flows from higher pressure in the small balloon to the lower pressure in the big balloon, and hence that surprise result.
So why? What is going on? How can we form this into a science inquiry, so a scientific question? So the next slide will be useful for that. And then some of the elements of thinking like a scientist, scientific inquiry approach, will be encapsulated on this. Now, you'll see different versions of this, so don't get too bogged down about, you know, that things can be in a slightly different order or slightly different words. It's the overall feel of what's going on. So what you've done, we've done the top box, so we've observed, and we're going to ask a scientific question. So something like, right, why does the air move from the smaller balloon, so it gets even smaller, and push it into the other balloon? What's going on there? So the next stage there is thinking, right, let's have, that's not a very scientific question, I'm sure you've picked that up, but you get the idea that we have a problem that we're trying to solve. So we're trying to have some explanations of what might be going on there. So we might think, oh, it's to do with volume, or maybe it's to do with the rubber, or it's to do with temperature or particles or pressure or whatever. So we can start to come up with some predictions. Now, the key one is here. Now, you're not probably going to be doing science to this level with your stage 1 to 6 learners. I'm using it because I was hoping to pick something that you hadn't met before. So we've got our balloons, and we're thinking, right, if air has flown from there into there, it must be due to a pressure difference. So for some reason, the smaller balloon had higher pressure, internal pressure, than the bigger balloon. And what's happened now? The tap's still open. I can open and close it. There's no change because now the pressure is equal between the two balloons. So something is creating a bigger pressure when the balloon is only inflated to a small degree. Let's bring in other ideas. We think, actually, when I start to blow up a balloon, and you might have seen me struggle to get the smaller balloon started, you recognize yourself, to get a balloon started, it can be quite tough. And then once it gets going, you can then blow it up more comfortably. So there's something about, so I'm just sort of talking through my thinking here as we make an explanation and a prediction. There's something about the tension in the rubber, and it doesn't stretch evenly, and the inward force by the rubber is greater when it's only just starting to inflate compared to when it's really, really stretched and it's exerting less of a force. there's less of a force, the pressure is lower, which is what happened in the big one. So that's our explanation. Now, the next stage is when you think like a scientist, we need to test this explanation. If we've got a good explanation, we should be able to use it to be able to make other predictions and then test them. If we can do that, then it's a good theory, a good explanation. If it doesn't work, then maybe our explanation is no good. So what we could think of is, right, let's think of another situation when the balloon is really, really hard to blow up. And the answer, a good example I do, and if I'm doing it with older learners, I get the balloon and I blow it and I blow it and I blow it and I blow it and I blow it. And so it's right at the point of bursting, and it gets really hard at the end. And it's great fun to do in the class because the kids are all cringing because they think it's going to explode in your face, everything. So you get this huge balloon. I'm not going to do it because it's a bit of a faff, and I usually end up ripping the balloon and it all goes wrong. But you end up with this massive balloon instead of the little one, and you open the tap, and in this case it goes from big to small instead of from small to big. So what you actually find, that theory about the way rubber stretches, it was a pretty good explanation. So leading around to the last one in that cycle, do we accept our explanation? Do we want to modify, or do we reject it? Well, it was wrong. Well, in that case, we say it's good. We might want to do further tests, definitely. But so that is a process of scientific. That is thinking like a scientist. And we took it further. I've got a theory. Well, I give it to my peers. Right, Rainer, see if you can reproduce these results. See if you can get it to work in different situations, different balloons. And the scientific community peer assesses. So if I'm talking rubbish, they'll soon be on to me to point that out. And that's how the scientific process works. So thinking like scientist. Okay. Then we talk about different types of scientific inquiry. Let me just check the time that I'm all right. Not too bad. So the first one I'm going to mention is observing over time. So this might be something like the growth of a living organism. You're not taking a measurement, well, you could take measurement at one point, but you're looking over a longer period to see what happens. Or you might be saying, how does the soil in a field change over the course of a year or over the course of many seasons? Valuable stuff, soil. We are interested in that. So that's observing over time. And there's an example, I just picked out one example at random. There's lots of these in Max Science. So stage 4, unit 2, in the solids, liquids and gases, we've got changing state. So we're looking at the changes of water as it's heated up. And you can see already there starting to steam emerging. Don't worry what the cook is sprinkling into that. That's a bit of a distraction. So that's observing over time. Absolutely a type of scientific inquiry, finding out about stuff. Right, our next one is identify and classify. So this might be very useful if you're dealing, for example, with living things. So if we had a group of different vertebrates, so it's some fish and some birds, and we split those up, okay, those are clearly birds, those are clearly fish, and what you're doing is you're learning about their biology. Those are the similarities. There are differences between them, and it's helping to deepen your scientific understanding. You might use it with materials, and that's the example I picked right from stage 1 in what's it made of, which is a materials unit, and the learners are making a sorting poster, and in this case they're sorting materials depending on their properties, what they're hard, soft, bendy, what you can choose the criteria you want. That's the beauty of sorting. So there's an analytical element to it even at stage 1. Absolutely. What else to say about that one? Yeah, I mean, if we can understand and classify materials, then we can start to think more about what would we use those materials for. So very, very useful skill. Right, next one is pattern seeking. Now, we picked this one deliberately because stage 6, unit 5, there's the unit caring for the environment, which is so topical. Hopefully lots of you are aware of the teenage girl from Sweden, Greta Thunberg, a climate activist, and become a real spokesperson for a generation. And he's capturing imagination of young people all around the world. And she's doing, a great job. She's reaching people, she's communicating in a message in a way that hasn't been achieved before, I don't think. And you can see on the spread from the Max Science book there, SOS, the planet Earth, SOS, how can we save the planet? And it is getting that serious. So it's from that chapter. And for the activity for the pattern seeking, it's actually a litter survey, which is a small part, but nonetheless important part of looking after the planet, caring for the environment. So in the litter survey, they're looking around the school and saying, well, is there more litter in one place than another? And what's it linked to? Is there more by the dining rooms? Is it more in the yard? And you'll see other prompts in there. So the fourth bullet point down talks about the litter bins. Okay, the litter might be terrible in the playground, and it might because the wind is blowing the litter everywhere, and kids are brilliant. They always put their wrappers in the bin and then they blow out. So it's trying to obviously looking for patterns and trying to understand what the science is behind those patterns. And then obviously, as a good scientist, you think, well, we think it's this reason, we think it's a badly designed bin. So then that leads you into a scientific question to then go through the inquiry process again. So lots of these things that you'll see in Max Science aren't necessarily closed. You can take them further. You can take them into other areas that you want, or to follow the student's interest, provided your head teacher is very kind and gives you lots of time in the week to do lots of exciting science and doesn't try and cram it into 1 hour a week or something, which is a challenge. So and next one is research. So this is research using secondary sources. So that could be books, the internet, leaflets, and so on and so forth. So one in Unit 5 of Stage 5, Earth's Movements, is researching a space scientist. There's lots of them. Galileo will be one of the most famous ones, an Italian scientist who some people call the father of observational astronomy. He's the first one that was really looking at the stars and the planets as well, and working out, well, why do they move like that, and making predictions. Right, if I'm right, if I understood this, that planet should be moving to there by tomorrow, and so on. Brilliant work. And also sort of often credited as being the father of the scientific method, so that scientific inquiry process that we've been talking about in this webinar. So we have a lot to thank him for. So you could research Galileo or anybody else, and that part of that chapter, there's an opportunity to do that. Now you'll just see popped up in the side a reference to some of the other skills, and with any type of research, and this is so important well, it's always been important, but we're so bombarded with information, it's probably more important now, is thinking about, well, this source or this book or this internet site or this YouTube video tells me this. Do I just accept that, or do I look from a completely different source and see if I'm getting the same method, the same message, or a different, something that contradicts, something that's broadly the same? The broader that the students will collect their information from and test the thinking and look for agreement, the more confident they can have about what they're learning and what they're right. So that's a very important skill. And then when you're looking at sources, right, who's actually put this website up about soil preservation? It's a chemical company which makes chemicals for farmers. So maybe they are giving a biased view, a slanted view, because what they really want to do is sell their chemicals to farmers. So let's have a look at the Soil Association, for example, or another Wildlife Fund for Nature, whatever, another source. Does it agree? And the last bullet point about recognizing, looking for bias and vested interest. So that's research. And then the one which is often most commonly, most thoroughly covered in many schools is the fair testing. So an example of a fair test investigation might be investigating the temperature, the effect of temperature on plant growth. So in this case, what you're doing is, let's say we had 2 plants, and we'll try 2 different temperatures. We'll try one at 20 degrees Celsius, we'll try one at 30, and we'll compare the growth of the 2, which grows most leaves, which grows tallest, whichever. To make it a fair test, to make our conclusion something that we can have confidence in, we need to make sure that our plant at 20 degrees C has had just as much chance to grow as the plant at 30 degrees C. So same amount of light, same amount of soil in the pot that they're growing in, same type of plant and age of plant, same amount of water each day, and whatever. So trying to make everything else fair. So if there is a difference between how those plants grow at the 2 temperatures, then you could say that must, unless we've missed something, that must be down to the difference in temperature. So that is a fair test. So just picking one out there. Okay, stage 3, unit 3, flowering plants. They actually do their own, and you don't have to do just 2 plants, 2 temperatures. You can do a whole range of different plants, different temperatures to go further, and you look for patterns within temperatures. So it might, there might be a peak, maybe 22 is great, any hotter is not so good, colder is not so good. So you can really explore things. One thing about fair testing is sometimes it's, I said about keeping everything else the same, sometimes that's really hard. So if we were testing medicines, for example, say a treatment for flu, and you could, I might have flu, Rainer might have flu, so we both take the medicine, or maybe I take the medicine, Rainer doesn't. But is it actually a fair test? Because we're not the same person. So the way it works in medical trials is you'd have a huge sample, you'd do it on 1,000 people, and you give 500 of them the remedy, 500 you give a placebo, a false tablet, so they think they're getting the medicine, so the brain's working, I'm going to get better. Then you'd say, oh, actually, yeah, we had 70% got better with the medicine, and only 48% got better in the same time with the placebo. So that's the way to handle variables when you can't control them. So that would be something coming in much later, stage 5, stage 6, and obviously need to be built on as the kids get older. Okay, when kids are doing scientific inquiry, there is inevitably, if you choose, and it's a great opportunity to do lots and lots of talking. So the kids are developing their language and their thinking, they're testing their thinking, they're exploring each other's ideas, and they're talking and forming their ideas, and they're doing this in English, hopefully, and so it's a very powerful opportunity to develop the language as well as their abilities as scientists. So this is a neat little thing to develop this thinking and discussion and language development. So what we've got here is a table or a big sheet of paper, and in the middle of it we've got an oval, and we've got a set of post-it notes which you can't see. So if we think back to the balloon problem, if we use this oval and this table as a tool and the post-it notes, I'm going to say, right, now, what ideas might be useful to try and answer the balloon problem that we've just done? And say to the learners, it doesn't matter if you're not sure about the idea, just put everything down that you want, and then write it on a post-it note and stick it on the table. So one of them might write, oh, I think it's diffusion. Another one might say, oh, no, it's pressure, it's temperature, it's no particles, they're the key thing here. And no, it's to do with the rubber, I think it's to do with the elasticity, I think forces are involved. So they come up with all these ideas, and that's great. So that's a collection of ideas. Then the next stage in that is each learner might put 2-3 ideas each. That's absolutely fine. And then you start looking at the ideas in a bit more detail, thinking, right, for the balloons, how is temperature going to be useful in explaining why the small balloon got even smaller. And they chat about it, and they think, actually, I'm not so sure that's a useful idea right now, so I'm going to leave that on the other side. On the other hand, we think there's something to do with the way rubber stretches. I notice it's really hard to blow a balloon, so I think the rubber and how it stretches is really useful. So that idea we're going to move on into the centre because we think that's really useful. And another one that's really useful is this idea of pressure, because pressure is what might push water out of a hose pipe, or or air out of a bicycle pump, or water out of a water pistol or something like that. So we think pressure is useful. So you gather your most useful ideas in the middle. The other ones you come back to them if you want, but you leave them to one side. There might be other questions that you have before you can really get to the nitty-gritty of your explanations. So for example, you might say, actually, these balloons, are these balloons the same age, from the same place? Are they going to stretch evenly, those two balloons? So any other ideas you'd want. And then once you've collected those ideas together and you had a good old discussion about them, then that leads you to be able to make predictions. So rather than leaping straight into predictions, which often just end up being guesses or hunches, it explores the science, it looks at the ideas in a little bit more of a systematic way, and you're more likely to then get a prediction that is backed up with some sort of evidence or prior learning or ideas. So it does become a genuine prediction and not just a guess. It might be wrong, but that doesn't matter. You know, it's the process of doing that. Okay. When we're thinking of scientific inquiry, it's useful to think of it broken down into strands, and you'll see the Cambridge International Curriculum does this, as do many others. So the strands are ideas and evidence, planning, obtaining and presenting evidence, actually doing the activities, presenting the evidence, your tables, your graphs, whatever you say, and then the final one, considering evidence and approach. So that is, right, we've done these investigations, what have we learned? Have we learned anything that we can be reasonably sure of? Are we a bit unsure? Actually, we've proved something here. We were really, really confident that what we found out is right. And then considering approach, was the investigation we used the best that we could have done? Could there be other investigations that we would do which would help us to understand more about this problem? Or did our investigation not really tell us anything? Perhaps we didn't measure it, we should have measured it, you know, whatever it is. So those are the 4 strands. And when you look what sits underneath that, am I all right for time, Ryan? I think I am. Yeah, thumbs up. You can break each of those 4 strands down into sort of individual skills. So what we'll do is look at I can't see the whole thing. Planning investigation, it's all right. And the screen is cluttered. I can't see my own slides. So for the planning one, if you think about what goes into making a plan, well, until you made a scientific question, have a nice focus. How can you plan? So that's the first stage. Then you think about okay, let's thinking about predictions as you were doing with the balloons. That's very much part of planning. So it's not an aimless thing. You've got an idea of what you might expect and what you're trying to prove. It might turn out to be wrong, but that's valuable learning. And then the third part of that is starting to actually plan what you're actually going to do, be it a fair test or another type of inquiry. And then just unpicking one more. I'm not going to go through them all. You'll be sad to know. Unpicking the obtaining and presenting evidence. There's a whole load of things around that. So you might be comparing, you know, was the lion faster or was the human faster? In my case, it would be the human. I would be faster than that lion. If it was chasing me. You might be describing things. Measuring very much comes into this, teaching of scales and units. Presenting all of this as tables, as graphs, as charts, tally charts. You might be drawing diagrams as a way of recording your evidence. And the final one if you're investigating, you're carrying out work as a scientist, you need to think of, you know, the potential risks of what you're doing, and that is very much built into the scientific inquiry approach, and develop that over time, and that's good to do. So they're not just relying and blindly doing what the teacher says. What you ideally want the learners to do is to be thinking for themselves, taking responsibility. Well, you know, we've got two unknown chemicals here, and we're just going to chuck them together in a beaker. Actually, I don't know what they are. I'm going to wear some goggles, or I'm going to mix really tiny amounts, you know, just in case. Yeah. So just gradually getting an understanding and a feeling of safety and taking responsibility. So I mentioned earlier the science skill sheets, scientific inquiry skill sheets. So just saying a little bit more about that. So our strands of scientific inquiry, which, really sorry about that, I'm gasping, and Ryan put my drink at the other end of the room.
Sorry.
That's all right. So those are the 4 strands that you'll recognize from an earlier slide. So what the skill sheets do is they break down those strands into the skills, like I showed you 2 slides earlier, and then they think about, right, in a course for a 3-year period of learning and doing science and becoming scientists, where would we like to get them to in 3 years? So we have these things called 3-year milestones, and they're really, really useful because they focus about your end point of what you want kids to be able to do at the end of stage 3, at the end of stage 6, and so on. And then feeding each of those 3-year milestones are a series of skill sheets, and they're focused activities. You'll find 3 of them for each unit of Max Science. They'll be rooted in the context of that unit. You know, so if you're measuring shadows, if you're doing about how shadows change, that's a really good opportunity to do some stuff on measurements. So, and then there might be some extra context. So if they can measure shadows correctly and learn that skill in the context of the unit, if we give them something completely different to measure, can they still do it? Can they apply it? Really important skill. And these skill sheets are completely optional. So you look at where your learners are, what they need to develop, and you can think, actually, they're great at this. I don't really need any more support to develop this. Or you might think, you know what, their measurement, I think we need a bit more focused work on this. Oh, look, there's a wonderful skill sheet to help me. And some of them are really, really quick, you know, 10 minutes, something like that. Some you could extend to be a whole lesson. You can use them absolutely flexibly to fit the needs of your learners. Okay, a few quick tips as we draw to the end of just helping to get scientific inquiry going in your classroom. So make it interesting, make it engaging. So it might be the learners' questions, it might be something that surprises them. That's why I picked the balloon thing. I thought you might find that, you know, amusing, interesting, maybe not at this time of the day. So that always helps. The learners' own questions are great, although they do tend to be quite wide-ranging. So you sometimes have to be a bit selective with them. A really, really useful tip, which I actually didn't learn this at university when I was training. It's sort of the penny dropped, and this is my first year of teaching. But if I started my planning with the question in my head, what do I want the kids to learn, or what new skills do I want them to have? That led me to plan better lessons than if I think, what do I want them to do? So do I want them to boil water? Well, yeah. Actually, what I want them to do is to learn about how water changes as the temperature changes, or I want them to learn how to measure temperature accurately, whatever that is. So it's a bit of a mindset thing. Another thing the research points to really strongly is if you can focus on 1 or 2 skills maximum, and you've got more chance of embedding that skill. Otherwise, the children just get overwhelmed with it all. So you don't have to do full investigations. You don't have to plan everything, always ask scientific questions, but do predictions. If you've got a focus of measuring accurately, you could skip a lot of the planning, get straight onto the activity and really focus on the measurement side and the units. Focus is good. You might do full investigations, but the focus is good when you're trying to develop a specific skill. And but again, just increasing focus. If you have your objectives for your learning, whether they're something you share with the pupils or they're just for your own purposes, it is absolutely fine to have an objective for the scientific knowledge and understanding and an objective for the skill. So in that one that I've put on the screen, today we're learning how shadows change throughout the day, and we are learning to measure length accurately, or something like that, just an example. Okay, there's a skill sheet. I think I've covered most of the information about that. One thing you will see is that they are all accompanied by teacher notes. So the bit of the background for it to help you if you're not completely confident in the science or the technique behind it, so it's teacher notes, and to suggest to you how you might want to use it as well. They look a bit different to that screenshot there, but the substance is there. So just very quickly summarising there the main points from Max Science, based on the Cambridge International Curriculum, but takes it a lot further, very much with additional language learners in mind, based on research, inquiry driven, and there's a full suite of materials that the schools can opt in or out of, whichever they want. So student books, teacher's guide, workbook, so something that the learners are actually doing their stuff in, a journal for use at home, and a teacher's presentation kit, which includes the additional digital resources, the skill sheets I spoke to earlier. So that's Max Science. So I've gone a couple of minutes over, so I apologise to you all for that. And so what we've done, we've tried to do an introduction to scientific inquiry. So I'm going to tick that. We've talked about that thinking like scientists with the balloon problem, and we've talked about other examples as well. Tick. Different types of scientific inquiry, pattern seeking research, fair testing, so on. Another tick. And getting that balanced. So you've got a lovely, vibrant, busy classroom, kids all hyper engaged. Sounds great. Make sure that they are learning as well. And if you've got something specific you want them to learn, I keep using the example of measurement, but it could be anything. Make sure by the end of that you've got an idea. Well, can they actually measure? That's what I wanted them to be able to do at the end of this. Can they measure to the nearest millimetre accurately? Tick. So I'm going to finish there. I'm going to hand briefly back to Rainer. Thank you very much for listening, and we are just about ready for questions.
Thank you so much, Pat. Really informative. We did this in the morning as well, so we had a lot of interest in inquiry-based learning because it's very much a key element of a lot of science lessons at the moment. So thank you so much for the webinar. If you do have any questions, feel free to write them in the question box that you'll see. And then what I'll do is hopefully Pat will be able to answer those questions. So if you have any questions, feel free. Otherwise, if you have any questions regarding Max Science or the CPD certificates or anything in relation to what we've delivered today, then you can see our email address, international.curriculum@macmillaneducation.com. So feel free to message us there. So we'll just wait for a few minutes to see if there's any questions, and then we'll take it from there.
I mean, maybe I've done such a good job that there's no questions. I've answered it all. There usually is. There usually are questions. Oh, that's better. I can see.
There's sometimes a delay.
That's...
Okay, so we've got one question, which is, what might teachers struggle in using scientific inquiry in the classroom?
Yeah, that's a good question, because it'll depend often on what those learners and those children are used to. So, for example, if they are really used to sitting down in rows, being instructed, to suddenly launch into scientific inquiry with lots of talking and thinking, it can be quite a culture shock. So that can be, depending on your school and what your children are used to, quite a challenge. So what I would say is, if your school is a bit like that, there'll be, you'll need to be patient. You'll need to introduce it little bit by little bit. And at stage one, the skill sheets are very gentle and just little activity. So you're not launching into a whole investigation or anything like that. You're just doing little practical skills, little thinking skills, and then maybe the full investigation might come later. But just asking questions is another good route into it. Chuck a bucket of water out on the pavement and ask the children what's going to happen to the water, or say, right, we're going to come back and have a look at that later, and you come back and the puddle's gone. What's happened? So that launches you into scientific questions. So that's a good way of overcoming one of the challenges. Good question. I like that one. When I've been working in schools with this and other new techniques, it's often easier with the younger children to get them into the habits early on, where it is no doubt tricky that we if you launch in with class, say, doing GCSE, so they're 15, 16-year-olds, and they've been very used to not discussing and not doing inquiry based, so you try and introduce it, then it can be really hard work. They can be quite reticent about it. So the idea is, actually, you do what you can with those kids, but get them in the right habit as early as possible, and the rewards are huge.
Great. And we've got another question which says, what would be the ideal class size for applying the technique, and how many students?
You're going to go and tell this to your head teacher. Pat says, yeah, I think I think too small a class is a class can be too small in that you don't get that range of ideas, and it's not as dynamic as you like. So I think 20 is an absolutely wonderful number. You can do bigger experiments, you can combine your results, you've got all sorts of ideas. 30 is fine. It just, each child tends to get a little bit less attention, but I know many of you will have bigger classes than that. That is one of the strengths where group work comes in, because although you might have, say, 60 in your room, and you might have a teaching assistant or you might not, those 60, if you're really organized in that group, they can be working in groups of 5 or 6, so they're all getting that individual sort of activity and thinking and talking and doing. Obviously, the bigger the group, the more organisation it takes from you, and the more more stress you're going to have trying to get around all the groups to listen to what they're saying, to help them, nudge them, prompt them if they get stuck, and to manage all this activity. So maybe the answer is, ask your head teacher for groups of 15. They say, no way, we're going for 30, and you say, I'll do a deal, we'll have 20. Maybe that's the approach.
So we've actually got a question that's about class size again. So how can we use the method with a class of 30 in a better and disciplined way when all the 8 and 9-year-olds want to tell, when they all, I assume, want to share their answers together?
Yeah, I mean, that's 30 is interesting you've picked that, because that's a really typical class size in lots and lots of countries. It's about habit of work. And I think it's often about ground rules. So if you're having a class discussion, the example I used was the sheet of paper and the post-it notes. So rather than this chaotic discussion of everybody shouting out, it slows it all down. Right, if you've got an idea, put it on a post-it note, stick it on the table, and then appoint a person in your group of 5 or 6. Right, they're going to read it out, and then each person has an opportunity to say, I think we move it into the centre because I think we leave it on the outside. So it's about structuring it a bit more. children need training in that. I absolutely accept. The first time you do that, if the kids just do it without any problems at all, it's miraculous. I've never seen it. You know, start small. I wouldn't be launching straight into a big discussion. I would just say, you know, just get them used to talking in pairs. Right, you've got 1 minute to discuss an idea on one post-it note with your partner and decide whether you agree or disagree. 1 minute, the clock's ticking or the egg timer, the sand's dripping through the egg timer. And if they can do that, then that allows you to do something a bit more ambitious next time. And I like mixing kids up as well, but that's very much down the road of once they're used to working in groups. In terms of how you set out the room is really, really important. All these kids moving around, you know, you might want to say, okay, I only want one person from each group away from their table at any one time. They might be fetching equipment or going to ask the teacher something. You know, it is very much about routines and setting down the guidelines, and you know, and they need a bit of work to establish in the early days. You know, set your ground rules, set them off, stop them after a few minutes, lots of praise. Groups 1 and 3 have followed the ground rules perfectly. Group 3 and 4, remember it's only one person. Okay, carry on now. So it's very structured, takes a lot of input, but the rewards are huge when you've perhaps done that from stage 1, or your colleagues have, and you know, and you can get your 8-year-olds and 9-year-olds come to you, and they're already, once they've got used to you, they're quickly into it. A long answer.
Great answer. Perfect. I think that's all for the questions for now. So just to mention, the session will be recorded and available on our YouTube page, which is Macmillan Education International Curriculum. And Pat has delivered 2 previous webinars for us, including this one, which will be available on the page. So please do feel free to check that out as well. Also, please feel free to email us with the email address for the CPD certificates as well, and we will be in touch with you. So just to say thank you so much to Pat for a great session, and also thank you for joining. I know teachers have limited time to join sessions, so we do really appreciate it. We do have a second webinar for science on the 5th of November. So we will be sending out links to that in the coming days. So be sure to check those out as well. So for now, thank you so much. And we will hopefully see you soon. Take care.
Okay, thank you very much. And thank you very much for joining. Thanks, Raina.
Thank you.